Okay, so it's 9 o'clock. So 9 o'clock is the time the lecture starts. So just to recap from the last lecture, so we went through and described some of these individual reservoirs that were a part of the carbon cycle, and we looked at the terrestrial side of this. So pretty much the exchange between the atmospheric box, or the atmospheric reservoir, and the terrestrial biosphere. And we looked at the exchanges between those, which we used to explain these annual cycles in CO2 recorded in the atmosphere. And we discussed how they were different in the northern hemisphere and the southern hemisphere, and why that might be. Okay, and that's related to the relative sizes of the terrestrial biosphere in the north and southern hemispheres. We also noted that we can't explain kind of where all our emissions have gone, okay, by just adding up what we've burnt and then kind of comparing that to what the concentration in the atmosphere is. Okay, so some of it must have gone into the ocean and some of it must have gone into the terrestrial biosphere. So even though we've been chopping down a bunch of trees, the biomass in the terrestrial biosphere has been increasing. But today we're going to be talking about that other sink, that other place where the carbon that we're burning is going. We're going to be looking at the ocean. So I asked you guys to watch a video that kind of went over and described this idea that the concentration of a dissolved gas is proportional to the concentration of that gas, or the partial pressure of that gas in the atmosphere above that liquid. Okay, so this is sometimes called Henry's law. Well, I mean, it is always called Henry's law because it's Henry's law. So this basically describes the solubility of any gas in a liquid. So that's the solubility, so basically how much gas you can dissolve in a liquid, usually in kind of grams per kilogram, is equal to some constant times the partial pressure of that gas. Okay, and the partial pressure is effectively the concentration of that gas in the atmosphere. And we'll go through a demonstration that shows that in a bit. That constant is not constant, it's dependent on temperature. So at low temperatures you can dissolve, the solubility is higher, you can dissolve more gas in the liquid, whereas high temperatures you can't. So just think of it as your kind of like a cold beer versus a nice warm British beer. Okay, so if you go to Europe, you have a nice cold beer. It's very fizzy because it's got a lot of gas dissolved in it. If you go and have a beer in the UK, it's warm and flat. Okay, not a lot of gas dissolved in it. Okay, so there you go. The other thing that the video kind of went through was this concept of, or the idea of describing the concentration of hydrogen ions in a solution as this term pH. So pH is just basically another way of writing the concentration of hydrogen ions. It's not actually the concentration, it's the activity, but don't worry about that for this course. So the higher the concentration of hydrogen ions, that makes this pH term lower, okay, because it's minus log to the base 10 of the concentration. So the higher the concentration of hydrogen ions, the lower the pH, and the more acidic a solution is. Okay? So that's the thing that you should know. So today's lecture, we're going to be talking about this basically the carbon cycle in and into and out of the ocean. So the first thing, just to recap from last lecture, is that we are burning a whole bunch of fossil fuels, like 7.8 gigatons of carbon per year. We're also changing our land use, so like burning stuff, chopping down lots of rainforests and replacing those with cattle farms and whatnot. So we're getting about 9 gigatons of carbon per year we're adding to the atmosphere. But actually the atmosphere is not increasing by 9 gigatons of carbon per year. Okay? So some of it is going to increase the atmospheric concentration, some of it is going into the land, but also some of it, about 2 to 3 gigatons of carbon per year, is actually going into the ocean. Okay? So you can see here, that's expressed here, that these fluxes into and out of the ocean are currently not balanced. Okay? So if we didn't have this additional flux into the ocean, this would be the amount of carbon that's dissolving in the ocean due to this solubility of carbon in liquids or in water, and then some of it would be exsolving out again. Okay? But because these are not balanced at the moment, more is dissolving in the ocean than is exsolving out of it. Okay? So we're going to be looking at that for the rest of the lecture. And when we look at that, we're going to basically start to split up the ocean into a bunch of different boxes, just like we did with the whole carbon cycle. So rather than thinking of the whole ocean as one reservoir of carbon, okay, we're going to be thinking of it as a bunch of discrete reservoirs. So we've got the atmosphere, okay, that interacts with the ocean, so gas can dissolve into the ocean and it can exsolve out of the ocean. And then we have this surface layer of the ocean, which is this warm, kind of quite often less salty, buoyant layer of water that sits on top of the cold, denser, deep ocean. Okay? And that has some carbon dissolved in it. Okay, some of it will be dissolved as CO2, most of it is dissolved as other things. We'll come on to that. And then things that live in the ocean, so plankton, fish, all that kind of stuff. So the plankton will take up, at least the phytoplankton, so the kind of the photosynthetic algae will take up some of this CO2 that's dissolved in the water and produce organic carbon. That will kind of move up the food chain or food web. And there will be some amount of organic carbon in marine kind of like biology. Okay? So that's kind of, you can think of that as a separate box, even though it's kind of lots of individual little fish swimming around. And then we have a deep ocean. Okay, so the deep ocean has also lots of carbon dissolved in it. And that can exchange between the surface and the deep ocean through just mixing of water. Okay, so upwelling and downwelling of water. And then we also have this dissolved organic carbon pool, which is, I guess, there's also some of this in the shallow ocean. But this is just organic matter that has been formed in the surface ocean and has sunk down, okay, as discrete bits of organic matter, so bits of dead fish, bits of fish poo mostly. And as that breaks apart and starts to be effectively dissolved or respired by bacteria, some of those organic molecules basically break free of their cells and are kind of just floating around kind of free in the water, and that's this dissolved organic pool. Okay? So ultimately, some of the carbon from here and here makes it down into sediments, and the sediments have got a huge amount of carbon in them, but the fluxes into and out of those sediments is very small, or are very small. So just an idea of some of the chemical forms that we're going to be dealing with. So most of the carbon in the ocean is in this dissolved inorganic carbon. Okay, it says here that this is HCO3-. That's the most dominant chemical species of dissolved inorganic carbon. We'll see in a bit that there are other chemical species that are present. A small amount is this dissolved organic matter. Okay, and then the very small amount is actually things that are the living. Okay, so the things like whales and dolphins and cool stuff to look at. Right, so I'm not going to dwell too much on this side. I've already explained it at the beginning and also in the video to watch before the lecture. But basically, CO2, if you've got a low concentration of CO2 in the atmosphere, you'll have a smaller amount of it dissolving in the liquid. If the concentration is high, then it will dissolve more into the liquid. Okay? It's temperature dependent. So the amount that we can dissolve in the water, the amount of CO2, okay, so we've got CO2 gas in the atmosphere, the amount of CO2 aqueous in the water is going to be a function of the atmospheric concentration and the temperature. Okay, so the colder it is and the more CO2 there is in the atmosphere, the more the ocean will absorb it. And we can see this effect of temperature in the air-sea fluxes of carbon dioxide. So this is how much carbon dioxide is going into and out of the ocean. So blue is going into the ocean, red is coming out of the ocean. And you can see in regions of the Earth where the water is very cold, okay, CO2 is being drawn out of the atmosphere and into the water. So places like the Arctic, North Atlantic, the Southern Ocean, very cold places, okay, lots of stuff can happen. Okay? But if we look at some of the warmer places, okay, so this is along the equator, in the kind of like Arabian Sea, we're also because the water is warm here, okay, it can't hold as much CO2, so CO2 is coming out of the water into the atmosphere. These are also regions where we're bringing water from the deep ocean to the surface. And we'll see later that the deep ocean has got a higher concentration than the surface ocean. Okay, so if you bring water that's got too much CO2 in it to be in equilibrium at the surface, if you bring it to the surface, it will try and reach equilibrium by kind of lowering its concentration by putting CO2 into the atmosphere. Okay, so that is basically these fluxes here. And these are out of balance with each other at the moment because there are, we've increased the concentration in the atmosphere. Okay? They would also naturally be slightly out of balance, okay, because if you think about the total fluxes into this box here, we've got a flux out. Okay, so some carbon will come in here and out here, but because this flux is very, very small, it's kind of like 0.2 or 0.3 gigatons per carbon unit, that's the difference we would expect there. Okay? Right, so when it dissolves, so CO2 doesn't just dissolve in water. So CO2 comes into the ocean as CO2. Okay? Now some of that will just dissolve, so that just means that the CO2 molecules will be floating around amongst other water molecules. Okay? But some of that CO2 will actually react with the water. Okay? It will react with the water to form this molecule here, which is carbonic acid, which is a very, very unstable molecule. It breaks apart rapidly, and it either breaks apart back to CO2 and water, okay, or it breaks apart to form this bicarbonate ion and a hydrogen ion. Okay? This molecule also is unstable, okay, so that can break apart and form a carbonate ion and another hydrogen ion. So we can see here that if we add CO2 to water, we actually end up forming things, okay, that have got, that produce hydrogen ions. Okay? So that means that they are going to acidify the water. Okay, and I've got a demonstration to show that here. So, not done this in this lab, so might, you know, make a horrible mess. So this is water, which I think is from the taps in the Grant Institute. It's been lying around in my office. It's either from the taps of the Grant Institute or it's from a stream on Arran, where I did this demonstration last. So this is just, floor's wet. You take care when you walk out. So this is, talk amongst yourselves. This is a soda stream. I'm sure you might have, they were popular in the 80s, I guess. It makes fizzy water. So I'm going to start out, so just to, as a control in my beaker for science. So this is, what's this? Lemon curd. That, I've washed it thoroughly. So what I'm going to do is take my soda stream and carefully okay, so that's just, I just inject CO2 into the water. Okay, so now this is fizzy water. So all that I've done is I've added CO2 to the same water. Dum, dum, dum. Science beaker number 2, which is cranberry with Cointreau. Cointreau? Very fancy jam that I have. Right. So that was exciting. I'm sure you'll agree. So I've got here some methyl orange, which is slightly toxic, so don't drink this. So if I put this in the, put a couple of drops in there, you see that that's gone kind of orange. Whereas this one is more of a reddy colour. I know it's not the most exciting science experiment that you've ever done, but this is just to demonstrate. Okay, you can see they're not the same colour. Happy that they're not the same colour? Not the same colour. Reddish, orange, yellowish, orange. Yeah? So this is just to demonstrate that this reaction at the top here, okay, adding CO2 to water, Okay? That makes it kind of acidic. Yeah? The next demonstration is slightly more dangerous because I've only got this metal spike. So what I'm going to do is I'm just going to suck up some of this water. Suck it up. Here we go. Right. Right, hold that there. And with this one, what I'm going to do is I'm going to do exactly the same thing, except once I've sucked it up, oh, suck it up, suck it up, suck it up. It's quite hard to suck up fizzy water because it just keeps on bubbling like a little, right. Maybe that's a bit too much. Okay, so now what I want you to do is hold this sharp stick. It's basically the only stick I have or could find. So the sharpness is not important. But there's in this one, steady. What was it in this one? In one of these, yeah, it was in this one. In this one, I've made a hole in the plungery thing. So I'm going to pull the plunger out. Okay, I'm going to stick that on the end. So I'm going to make a vacuum in here, but to hold it in place, I need a stick. Okay, there's got a hole that will appear. It will become obvious, right? Okay. Stick it in the hole. Down, in the hole, in the hole, in the hole, in the hole. Come on, in the hole. Here we go. Okay, right. There we go. So now what we've got here is I've basically lowered the pressure in this tube, right? Okay, so this is a vacuum. So as you see, it's extracting all of the bubbles. Okay, so now CO2, because I've lowered the concentration of the gas in the headspace, although this one, I guess this one doesn't really have headspace as such, it's got a little bit of headspace. The CO2 concentration here is quite high, okay? But by lowering the pressure in here, I've therefore, even though the concentration, like the percentage of the molecules in here that are CO2 is probably the same as the percentage of the molecules in here at the CO2, the partial pressure is much lower, okay? So hopefully you might be able to see, might try that again, and try and suck it some more, reduce the pressure, right, again, do me again, ready, come on, to the hole, yes, Jurassic Park. Ow. So hopefully these kind of, can you see that there's a slight difference in colour now? Anybody? Slight difference in colour. So this one's gone a little bit lighter. So by taking the CO2 out of the water, we're unacidifying it. If that kind of makes sense. Some sense being made? Okay, fun times. Right. I'm going to put these somewhere safe. Not sure. Didn't really think about this through in terms of, I should have bought lids. That would have been sensible. That's going to leak everywhere. All right. Right. So that was to demonstrate this idea that when we have CO2 dissolving in water, okay, it's going to not just stay as CO2, it's going to change into these different species. Okay? It's going to acidify the water. Okay? And then the second part of that experiment was just to demonstrate this idea of this Henry's law, in that the concentration, okay, in this case we're basically using pH, or acidity, as a proxy for the total amount of carbon dissolved in the water, is dependent on the... did you pick up a thing? You picked up a... okay, right, anyway. Is a proxy for the concentration. That concentration is dependent on the partial pressure of whatever's in the atmosphere. Okay? Just to point out that, see this reaction at the top, kind of this guy, or these guys go to this guy, goes to this. Sometimes it's written like this, okay, in terms of three separate reactions, where you have one reaction that goes from CO2 to carbonic acid, then the carbonic acid can break apart to this. So there are three separate equilibrium reactions. Now, if you actually look at what we actually have in the ocean, okay, in terms of the relative abundances of all of these different species, you can see that most of it is actually this bicarbonate form. Okay, so most of the CO2 that dissolves in the ocean actually reacts with water and then works its way through and becomes bicarbonate. A little bit, maybe 9% of it, makes it all the way through and becomes carbonate ion. Okay, so that will result in 2 hydrogens being released for 1 CO2. Only a tiny amount actually stays as CO2, okay, which is really important. And even like a tiniest, like almost none of it, this is almost undetectable in the ocean, this carbonic acid as a molecule. So quite often we group together CO2 and carbonic acid as one term. So you might see this written as CO2 star, okay, with a star after the CO2. That's just those two guys added together because this is so insignificantly small in terms of its concentration. So if we look at how these change with pH, if you go back and look at these reactions here, okay, imagine rather than adding CO2 to the ocean, okay, to acidify it, okay, I imagine we just added hydrogen ions to the ocean or took hydrogen ions away by either adding hydrochloric acid to the ocean or adding sodium carbonate to the ocean, something like that. That would remove, or I guess sodium hydroxide would be a better example because it doesn't have carbon in it. If we could independently change the pH, okay, you see if we added lots of hydrogen ions, so if we made the pH low, concentration of hydrogen ions would be high, that would force all of these reactions over to the left-hand side. Okay? So if we had a really high pH, we'd have a lower concentration of carbonate ion and a higher concentration of CO2. If we could make the pH really high, if we removed lots of hydrogen ions, these equilibrium reactions would go back towards the right-hand side. Okay? So we'd then promote having more carbonate ion and less CO2. And that's what's shown in this diagram here. Okay? So for any kind of one pH in the ocean, so at low pHs, we might expect to have more of the total dissolved inorganic carbon be CO2. At a high pH, more of it should be carbonate ion. If you look at the actual pH of the ocean, is around 8. Okay? Most of the dissolved inorganic carbon is as bicarbonate ion. A tiny amount is as CO2, maybe 1% or so, and about 9% is as carbonate ion. Okay? Now this turns out to have a really important, impact on the whole carbon cycle, because once this carbon dissolves in the ocean and then it splits apart into these different chemical species, okay, only the CO2 aqueous can interact with the atmosphere. Okay, these other kind of chemical species don't have a gaseous form. Okay, they're ions, so they're kind of like they like to stay dissolved in the ocean, whereas the CO2 is a neutral molecule, so it can kind of like get out into the atmosphere. So this means that if that Henry's law, in terms of the concentration in the atmosphere and the concentration of dissolved, only applies to the CO2 in the atmosphere and the CO2 aqueous in the ocean. It doesn't apply to this other pool of carbon. Okay? Which means that for any kind of one kind of amount of stuff that you can dissolve because of the temperature for the solubility of CO2, you can actually store a whole bunch more carbon in the ocean. Okay? It's kind of like a secret hiding place for carbon. Okay? The atmosphere can't see this. It can only see that. And this is the impact of that. Okay, so now instead of on the same plot as before, but instead of as relative abundance on the y-axis, I've put total amount of carbon in the ocean. Okay, so if you fix the atmospheric concentration, okay, at low pH, okay, almost all of the carbon in the ocean is as dissolved CO2. Okay, because those reactions are going all the way to the left-hand side because there's loads of hydrogen ions knocking around in the ocean. Okay, so that forces those equilibrium reactions to the left-hand side. So you can see that the amount, okay, is just due to the concentration in the atmosphere and the solubility. Okay, in fact, the size of this, the height of this green bar is the same all the way across this graph. I know it looks really small up here, but that's because it's a logarithmic scale. Okay? So the thing that determines the height of this bar is just the solubility of CO2 in water. Okay? Now, as the pH gets higher, the hydrogen ion concentration gets lower, so those reactions move over to the right-hand side, and we can start to store more and more of our carbon in these other species. Okay, so that means that the total amount of carbon we can store in the ocean goes up and up and up and up and up. Okay, and you can see this is a logarithmic scale, so at high pHs we can store huge quantities of CO2 in the ocean. Okay? If this wasn't true, the planet would be totally fucked. Okay? Because all of the CO2 would then be in the atmosphere, and we'd have a runaway greenhouse gas effect, and the planet would become too hot to become habitable. Okay, we'd end up like Venus, which is not a very nice place. Okay? Anyway. So the pH in the ocean is really critical because the pH determines how much carbon you can store in the ocean versus the atmosphere. So so unfortunately, by adding CO2 to the atmosphere, okay, that produces hydrogen ions in the ocean because the CO2 dissolves, produces hydrogen. That has the effect of lowering the pH. So not only are we putting CO2 in the atmosphere, okay, we're also acidifying the ocean, which has other nasty effects on kind of marine life. But I think the most important effect is it reduces the capacity of the ocean to take up CO2. Okay, because it lowers the pH, which means we can store less carbon as these other species, as bicarbonate ion and carbonate ion, which is annoying. So to see if we can understand this, okay, we're going to do some maths, because if you can work through kind of the maths of something, kind of it does suggest that you have a good idea of what's going on. Okay? So if we think about the first kind of part of the problem, imagine the ocean is at 4 degrees Celsius. We can work out, reading off that solubility graph, the solubility of CO2 in water is 3 grams per kilogram per atmosphere of pressure. Okay, so at 1 atmosphere pressure. So you can kind of ignore that because the Earth's surface is almost always at 1 atmosphere pressure. So if the CO2 concentration is 400 parts per million, then we can work out the CO2 concentration of CO2 dissolved, okay, is that solubility times the concentration in the atmosphere, okay, or the partial pressure in the atmosphere, which is 400 times 1 atmosphere. So that gives us, for every kilogram of water, we'll have 1.2 milligrams of CO2. Okay, work through that calculation if you want to. We can work out how many moles of CO2 that is, because number of moles is the mass of something divided by its molecular weight. Molecular weight of CO2 is 44. Tells us how many moles we've got. We can then work out how much total carbon that is. Okay, if we know the mass of the ocean, we know the concentration. Okay, so the total mass of carbon in the ocean is therefore the mass of the ocean times the concentration. It gives us this large number of moles here. We can convert that into amount or mass of carbon. Okay, so that's the number of moles times the mass of carbon, so we times it by 12. It's a common mistake that's made with looking at the carbon cycle is confusing mass of CO2 and mass of carbon. Okay, so there's a factor of 3 and a bit difference because CO2 has got some oxygens in it. Those oxygens weigh something. So we can do that. We can work out how many grams of carbon we have. It's 4.5 times 10 to 17 grams of carbon. That gives us 450 gigatons of carbon. Okay, that should be in the ocean. Now we know that our amount in the actual ocean is about 38,000. So this number is very small, and that's because only 1% of the carbon in the ocean is as this CO2. Okay? The rest of it is just these other inorganic species. So if we assume that only 1% is this, so the 99% will be kind of the other stuff. So we can times this by, or divide by 0.1. So this tells us if we make all of these assumptions, we should have 44 1,800 gigatons of carbon in the ocean. Okay? So that's not how much carbon there is in the ocean. So one thing I want you to do is to go onto the Learn site and look at the discussion forum. And there's a series of questions, or one particular kind of post, which basically goes through this, well, asks you to go through this and try and work out why these numbers don't match. Okay? And then you could do another calculation which might make them match a little bit better, and that also won't match, and they want you to think about why that is. Okay? So that's for you to go through on the discussion forum. I'll point that out at the end of the lecture. Right. So the point I've been trying to make is that basically only this tiny proportion here can exchange to the atmosphere, so we can store loads of this stuff in the ocean. Okay? So if we keep this proportion constant, so this the proportion of gaseous CO2 to dissolved, that's that solubility constant in Henry's law. So if we just change the speciation, okay, so if we change the pH by a little bit, lower the pH to make us have a little bit more of this stuff here, okay, we have to keep this ratio between this guy and this guy the same, okay, because that's a constant at any one temperature. So just by changing the speciation between these different forms of carbon, we can have huge effects on the atmospheric CO2 budget. Okay? So that kind of summarizes that part of the lecture. Okay. So I guess fortunately, this change in CO2, which I guess we haven't really mentioned so much, is buffered by alkalinity. So if you have just tap water and you add some CO2, the pH can change quite quickly. Okay? But if you have ocean water, or water that's got a high alkalinity, so it has lots of kind of salts dissolved in it, lots of magnesium carbonate, things like that. If I did this experiment with actual mineral water, it wouldn't work. Okay? Because the alkalinity in mineral water, or the alkalinity, if I did this in seawater, this experiment wouldn't work. Because the alkalinity buffers the pH change. Okay, and you guys should be thinking about that for your ELE practicals. Okay, so having a high alkalinity is really good because that buffers the change in pH when we add CO2. So it basically protects us from the effects of adding CO2 to the atmosphere and ocean acidification. Okay. So now if we move on, I mean, we've just been talking about the exchange between the atmosphere and the ocean and the surface ocean, and I guess thinking of the ocean really as one big box. But actually, if we look at a profile of the total dissolved inorganic carbon, so this is the sum of dissolved CO2 plus the concentration of the bicarbonate ion plus the concentration of the carbonate ion. If we look at that sum as we go down the water column, you can see that in the surface ocean, there's slightly less dissolved inorganic carbon than there is in the deep ocean. Not by much. So if you look at the scale on the bottom, it doesn't go to 0. Okay, the concentration is about 2,000 at the surface. It's about 2,300 at depth. Okay, so it's higher concentration in deep water, but not by much. Okay? But still, there is an enrichment as we go down into the ocean. So basically, we're going to be looking at now these fluxes between the surface ocean and the deep ocean. So trying to explain why the deep ocean has got more carbon in it than the surface ocean. So I guess, again, just to recap, that the surface ocean is basically a lot less dense than the deep ocean, which keeps it very much separated. It's actually quite hard to mix between these two layers. And the surface layer tends to be a bit warmer, and the bottom water tends to be a bit cooler, because bottom water, or the deep ocean, forms when water sinks from the surface in high latitudes around the North Atlantic and in the Southern Ocean, where it basically loses moisture to the atmosphere, so it becomes a bit saltier, and it also loses heat to the atmosphere through evaporation. So the water in the deep ocean is cooler, okay, when it is at the surface, and then it forms into the deep ocean. So that means that actually maybe some of this change in concentration, okay, is just because when this water was at the surface, it was colder than this water that is at the surface now, okay, and that means that it could dissolve more CO2 in it. Okay? So that's one thing, one reason why we have slightly more CO2 dissolved, or more carbon, sorry, total carbon dissolved in bottom water. Okay, and that's because deep water forms in these two places, mostly around kind of Greenland and some in the Labrador Sea. Quite a lot forms around Antarctica. These are very cold places, okay? Which is why I used that number of 4 degrees Celsius for the calculation, okay? Because that's kind of quite a reasonable approximation of the average temperature of the deep ocean. And that's where most of the carbon is in the ocean, because the deep ocean is very, very big compared to the surface ocean, because the ocean is really deep. Okay, it's 5 kilometers deep, which is very deep. And you can see here that this is the total section, basically a slice taken through the ocean vertically from the north to the south over here. And the colours on this plot here are the concentration of total dissolved inorganic carbon. Okay? And you can see that we're taking, and that you can see the surface ocean here has got a lower concentration. Okay? And in these higher latitude regions, it's got maybe a little bit higher. That might be because of temperature. And you can see that, as that water sinks down and gets mixed down into the ocean, it brings that concentration from up here down into the broad ocean over here. Same for the Southern Ocean. The Southern Ocean seems to have a little bit higher concentrations, and it brings that water with that higher concentration down with it. Okay? But as that water is moving along, okay, you can see that it doesn't actually keep the same concentration. It increases in its concentration as it flows along this path of water here. Okay? So it seems to be the longer that water is in the deep ocean, okay, the higher the concentration of dissolved inorganic carbon is. Okay? So what we're going to do now is look at some of these fluxes in between the shallow ocean and the deep ocean. Okay? Now, the biggest of the fluxes is just mixing between the two layers. So although I've said that it is quite hard for water to mix across this boundary, okay, it does happen. Okay? We have kind of lots of storms, lots of deep mixing, usually in winter. You can mix water across this, and if that water's got stuff dissolved in it, you'll be mixing that stuff across that boundary. Okay? There's also, rather than just general mixing in the ocean, there's kind of a large-scale circulation in the ocean, which is not so important right now. And if you do oceanography, this will become a larger part of the course. But the water that sinks in the North Atlantic goes down to the bottom of the ocean and then flows along the bottom of the Atlantic. You also have water sinking here. It's not really shown on this figure. And that kind of joins this flow path, and water flows around Antarctica along the bottom. It also kind of makes its way up into the Indian and the Pacific Ocean, where it gradually then upwells to the surface. Okay? So that upwelling to the surface usually happens at places along the equator, in regions next to coasts where you can get a type of upwelling forced by winds. And that's, by large part, the reason for these fluxes of CO2 to the atmosphere is because we're bringing water that's from the deep ocean, okay, that's cold and has got lots of carbon in it for another reason as well as it's being cold. And that brings up water that's got lots of carbon dissolved in it to the surface. It heats up, and then that carbon dioxide then wants to be in the atmosphere. So this explains why we have fluxes to the atmosphere in these regions. Okay? Now, so that's kind of this flux here. You can see that these basically the amount of water, okay, that's mixed across this boundary must be the same. Okay? Because mixing is a two-way process. You can't only mix water in one direction. Otherwise, you'd just pile up water on one side of your bathtub or something ridiculous. Okay? But because there's a higher concentration of dissolved inorganic carbon in the deep ocean, the flux, if you mix water evenly up and down, if you've got higher concentrations down here, that will cause there to be an increase in flux of carbon coming up. Okay? Right. But so you can see that there's basically a an upwards flux through mixing and circulation. Okay? So that upwards flux, if the concentrations are going to be kept the same, must be balanced by a downwards flux. And that downwards flux is driven by marine biology. Okay? So if we look at what happens in the ocean, in the surface layer, okay, we have lots of little beasties living. Okay, these little beasties are ultimately taking carbon from CO2, doing photosynthesis, producing organic matter. That organic matter goes to producing the bodies of these phytoplankton. It also gets eaten by larger organisms. Okay, so that creates packets of organic matter in fecal pellets, and those sink. Okay, down through the water. And if you've ever been to the ocean, you'll notice that the surface of the ocean is not covered by fecal pellets. Okay, so those fecal pellets must be sinking, not floating. And this means that there's a flux down of particulate organic carbon. That organic carbon, as it sinks down into the deep ocean, starts to break apart as bacteria start to respire all of that organic carbon. So those bacteria are respiring all of that organic carbon in that fish poo, and that produces CO2, okay, because that's what respiration is. It takes organic carbon plus any oxygen dissolved in the water and produces carbon dioxide. Now that carbon dioxide will then react with the water, okay, to form carbonic acid, to form bicarbonate ion and carbonate ion. So that has the effect of adding to the total inorganic carbon pool. So we basically think this is sometimes referred to as the biological pump, or the biological carbon pump. It's basically taking carbon out of the surface ocean, putting it in organic material, okay, and then making it sink down into the deep ocean. Okay. Now, yes, that's kind of explained here. So we're basically taking this inorganic carbon, we're producing this stuff sometimes referred to as marine snow. It's just fish poo and shrimp poo and other kinds of like macro life poo. It's just poo. Sinks down, breaks apart, forms CO2, okay, be degraded by bacteria, and that CO2 then breaks apart and forms carbonic acid and carbonate and bicarbonate ions. Which means that not only is the deep ocean enriched in carbon, it's also slightly more acidic than the surface ocean. Okay? Because we're adding CO2 to it, which means we're adding hydrogen ions. Okay? Now, at some point, we're going to make the ocean acidic enough that it's going to start to dissolve minerals that are bases. So it's going to dissolve things like calcium carbonate. So actually, if you go into the very, very deep ocean, okay, there's no calcium carbonate being preserved. It's all dissolved away. Okay. So if we have a look at some profiles now, we can see that the surface ocean has got lower concentrations of carbon. This is total carbon in terms of CO2 plus bicarbonate plus carbonate ions. But in the Pacific and the Atlantic Oceans, it's about the same, because it's just determined by the exchange with the atmosphere and the pH of the ocean. Okay, and then as you go into the deeper ocean, the concentrations are higher. Okay, those concentrations are higher because carbon is being taken out of the surface ocean by life, being packaged up into poo, poo sinks, and then is basically eaten by bacteria, and those bacteria respire it back out as CO2. Okay? If you remember one thing, it's going to be poo sinks. And you can see the effect of that having on pH. Okay, so you can see that pH is lower, which means it's more acidic in the deep ocean. Okay, and that's because of all of this carbon that's being added. Now, if you look at the difference between the Pacific and the Atlantic Ocean, you can see that the Pacific is got a higher carbon concentration and a lower pH. Okay, and that's because by the time the deep water has got to the Pacific, okay, it hasn't just kind of formed in the Pacific Ocean. It formed over here, sunk from the surface ocean, and has flowed all the way along down through the Atlantic, through the Southern Ocean, okay, and then eventually up to here. So as it was doing that, it was constantly having organic matter raining down into it. Okay? So you can think of it as basically an age of the water. So it's been a longer time since the water here has been at the surface, so it's had more time to accumulate carbon from raining down from the surface ocean. Whereas in the Atlantic, the water's only had a relatively short amount of time to accumulate that carbon and that acidity. Okay? So the Pacific Ocean effectively has older waters. Okay? And in fact, we can actually radiometrically date how long that water has been in contact with the atmosphere by sampling the water and measuring how much radiocarbon's in it, because radiocarbon only forms in the atmosphere, but that's a story for another day. Okay, so so to summarize the kind of the story so far, so ocean circulation is really important for the long-term storage of CO2. Okay? Because if you think about, if we make this flow path, if we make that really, really quick, okay? If we make that a really fast-flowing conveyor of water, sinks down, if it flows really, really rapidly and then upwells again, then there's no time for that water to accumulate carbon. Okay? Imagine if it's really, really slow. If it's really, really slow, then it can accumulate really high concentrations of carbon. Okay? So if we have slower ocean circulation, we can store more carbon in the deep ocean. If we have faster ocean circulation, we can store less carbon in the deep ocean. Okay? It's also a function of how much biology is going on in the surface ocean. So if there's lots of biology going on in the surface ocean, that means that more carbon is being exported to the deep ocean. Okay? So over kind of timescales of the residence time of the deep ocean, so of the order of tens of thousands of years, we might be able to change how much carbon there is in the atmosphere by changing how much is stored in the deep ocean, okay, through these processes of changing ocean circulation and changing marine productivity. Okay, so these are changes that can affect climate on tens of thousands of years. And I guess also the, I guess to add that, I mean, the role of ocean circulation is important, but also ocean pH is important, okay, because that ultimately determines what proportion of the amount of carbon that's in the ocean can interact with the atmosphere. Okay. Yeah. Okay, so, yeah. So this is this idea that if we can acidify the ocean, or basically if we add CO2, let's just start from the first kind of principle. If we dissolve CO2 in the ocean, if we add CO2 to the atmosphere, some of that will dissolve in the ocean. Okay? If the ocean at the moment is at pH 8.1-ish, okay, by adding CO2, that means that these series of reactions will move over more towards the right-hand side. Okay, so we'll be adding hydrogen ions. Now, that will go towards acidifying the ocean a little bit. Now, it won't acidify it as much as, so if we add kind of 1 mole of hydrogen ions, that's not going to acidify the ocean by 1 mole, because some of this acidity will be taken up by the alkalinity in the ocean. Okay? So the alkalinity in the ocean is actually largely this, what's going on in this graph here. So alkalinity can be thought of as the sum of all of the chemical species in the ocean which have these multiple forms. Okay, which have these multiple forms of say, for instance, a neutral species, a singly charged and a doubly charged species. And as each one of these changes, it can exchange a hydrogen ion. So it's not just the carbon system that does this, but boron has borate ion and boric acid, okay, which can exchange CO2s with them, so exchange hydrogen ions. So if we acidify, if we're doing something that adds hydrogen ions, okay, alkalinity is the ocean's or the solution's capacity to take up those hydrogen ions and